going to work through a illustration or a problem that involves electrical currents flowing in electrical conductors. It involves Ohm's law, that relationship between current and voltage in an electrical conductor. It involves the concepts of resistance, resistivity, and impeding current flow. And it involves the concepts of power, energy dissipated when a current flows. So in this particular example, we're told that we have a 100-centimeter long, 1 square millimeter cross-section aluminium wire. And we're told that a 40 milliamp current is flowing in that wire. And based on that information, we're going to figure out a bunch of it. We're going to figure out the number of electrons that are entering and exiting the wire during that 10 minutes. We are going to figure out the velocity of those electrons that traverse the length of the wire. We're going to figure out the resistance of the length of wire and the voltage across that length of wire. And finally, we're going to figure out the energy that's dissipated in that length of wire over 10 minutes. So that's a bunch of things that we're going to figure out, compute, based on our understanding of currents, Ohm's law, resistance, resistivity, power, and energy. So let's work through this problem. So over here on the left, I've made a sketch of the wire. So here's the 100-centimeter long wire. 1 square millimeter cross-section wire. And there's a current flowing in and out of the wire, 40 milliamps, 0.04 amps. There's electrons flowing in and out of the wire. And that happens for a period of 10 minutes, we're told. That's 10 minutes is 600 seconds. There's two additional quantities that I've written down here. Two additional quantities that I looked up here that are needed to solve this problem. One of them is the number of mobile electrons in copper per cubic meter, and that's this 2.1 times 10 to the 29 electrons per cubic meter. The second is the resistivity of copper, and that number is this 1.8 times 10 to the minus 8 ohms meters. So these are two additional numbers in addition to the quantities told in the problem that I'm going to need to use to solve this particular problem. So the first question is, how many electrons flow in on the left of the wire and out on the right of the wire in that 10-minute period? The way we'll calculate that is first figuring out the amount of charge that flows into and out of the wire. And then when we got the amount of charge that flowed into and out of the wire, we can find out the corresponding number of electrons that went in and out. I'm going to figure the charge simply from the definition of current. So electrical current is the amount of charge that's flowing through some cross-section of our wire divided by the time that it takes to flow through. So I can rearrange this equation to tell me the amount of charge that flowed in terms of the current that's flowing in the wire and the length of time that that current is flowing for. And I know both of these. It's 0.04 amps for the current, and it is 600 seconds for the time. And if I multiply these, that's 24 coulombs. 24 coulombs of charge flowed along the length of the wire during that 10-minute period. Now, that charge that was flowing along the wire was due to many, many, many electrons flowing along the length of the wire. Each electron carries a charge 1.6 times 10 to the minus 19 coulombs. And so now I want to figure out how many of those electrons, or 1.6 times 10 to the minus 19 coulombs, corresponds to a total charge that is 24 coulombs. So to figure that out, I'm just going to say that that total charge, delta Q I called it, is the number of electrons that flow down the wire times the charge that an individual electron owns. I'll call that E. If I rearrange this equation and rearrange it for the number of electrons, it's going to be equal to the total charge that flow down the wire divided by the charge of a single electron. And if I compute that quantity, I'm going to have 24 coulombs divided by 1.6 times 10 to the minus 19. That's the size of the charge of an electron. And if we calculate that number, I got 1.5 times 10 to the power 20. That's the number of electrons flowing down the wire in that length of time period of 10 minutes. The second question is, what is the speed of the electrons as they move down the wire? We know the number of them. Now, what's the speed? To figure that out, I'm going to use that relationship between this kind of macroscopic picture of current as just the flow of coulombs of charge, and the microscopic picture of current as the flow or motion of individual electrons. So the equation that describes that relationship between the micro and macroscopic viewpoints for current flow in terms of motion of electrons versus flow of charge is the following equation. I is the current, the flow of charge. And then over here on the right-hand side is the number of mobile electrons per cubic meter, the charge that each individual electron has, the average drift velocity of the electrons, Vd, and the area of the wire through which they're traveling. Now, I want to figure out the drift velocity. So that's the rate that the electrons proceed from the left to the right of the wire. And I can rearrange that in terms of the current, which I know, the number of electrons, mobile electrons per cubic meter, I've looked that up, the charge of an electron, I know that, and the area of the wire, cross-sectional area of the wire, we were told that. All these numbers I know. I can plug in these numbers, so 0.04 amps is the current. The number of electrons per cubic meter is 2.1 times 10 to the 29. The electronic charge, 1.6 times 10 to the minus 19. And the area is 1 times 10 to the minus 6 meters squared. And then if I carry out the calculation, I get a velocity, or I get a speed, a drift speed, a drift velocity for these electrons. It comes out to be 1.6 micrometers. That's 10 to the minus 6 meters per second. And so that's the speed of the electrons down the length of the wire. They are really, if you want to imagine those electrons moving down the wire, that contributes to that current that's 40 milliamps. There's an enormous number of these electrons. There's 10 to the 20, more than 10 to the 20 per cubic meter. So this is a huge swarm of electrons. But also these electrons are moving very, very slowly, very gradually along the length of the wire at about a millionth of a meter per second. Very, very slow speed. The next part of the question asks, what is the voltage across the wire? What is the resistance of the wire? Remembering that we know the current flowing through the wire. And so we're going to answer those two questions. We're going to figure out the resistance of the wire, and we're going to figure out the voltage across the wire. And we're going to do that by a combination of using Ohm's law and our understanding of resistance and resistivity and the relationship between resistance and resistivity. So let's go ahead and do that. I'm going to calculate the resistance first. So the resistance of a length of wire is equal to the resistivity of the wire. So that's dependent on the material of the wire. We know we've got aluminium and we know its resistivity times a geometrical factor. And that geometrical factor is the length of the wire divided by the cross-sectional area of the wire. It tells us that the longer the wire, the greater the resistance. The greater the diameter of the wire, the smaller the resistance, which makes sense, right? If you think of water flowing down a river, then the narrower the stream or the river, the greater the resistance to the flow of water. The longer the river, the greater the resistance to the flow. And those ideas, that analogy is just the same for electrons or current flowing through a wire. The longer the wire, the greater the resistance. The narrower the wire, the greater the resistance. Well, we know rho, L, and A. So all I've got to do is plug in the numbers for the resistivity, 1.8 times 10 to the minus 8, its units are ohms, meters. And then I've got to multiply that by the length of the wire, it's 1 meter, divide it by the cross-section of the wire, that's 10 to the minus 6 square meters. And if I carry out that calculation, I'm going to get 1.8 times 10 to the minus 2. So that's 0.018. And the units there are ohms. The ohms in the numerators, there's a meter here and a meter here, are cancelled by the meters in the numerator. There's a meter here and a meter here, are cancelled by the meter squared in the denominator. So that's the resistance. Now we can apply Ohm's law to get the voltage difference across the length of the wire. It's just by Ohm's law, the product of the current and the resistance. And we now know both of these. The current, we were told in the problem, is 0.04 amps. And the resistance you just calculated in the problem is 0.018 ohms. And so if I multiply these two numbers together, I got 0.7 millivolts. That's 7 times 10 to the minus 4 volts. There's a small voltage across the length of this wire. Typically, when currents flow through wires in an electrical circuit, whilst the two ends of the wires are not at the same voltage, otherwise no current would flow, the voltage difference between two ends of a wire is pretty small. It is often fractions of a millivolt. That's all that's needed to make the current flow along the length of the wire. The final part of the problem wants the energy that's dissipated in the wire as the current or the electrons flow along the length of the wire over this 10-minute period. I'm going to do this in two steps also. I'm going to first calculate the power that's dissipated in the wire, and then the energy, total energy that's dissipated in the wire. So the power that's dissipated in the wire is the joules per second that's dissipated. And then if I multiply that by the length of time that power is being dissipated, so joules per second times seconds, that's going to give me a total energy dissipated in the wire. So those are the two steps. The power dissipated in a wire is, so this is joules per second, is the product of the current and the voltage. It's just IV. Now, you can write this product in different ways. For example, you could say, well, using Ohm's law, let's replace the current with the voltage. So the current we would replace with V over R. So V squared over R is also the power. Or alternatively, you could replace the voltage with the current. So the voltage is IR. So that would yield an equation that is I squared R. So all three of these equations represent the power dissipated in the wire in terms of current, voltage, and resistance, or pairs of combinations of current, voltage, and resistance. I'm going to use I squared R. So I, we were told that in the problem, it's 0.04 amps. We've got to square that. And then we've got to divide that by the resistance. That was 0.018 ohms. So if I calculate this quantity, I got a value that is 29 microwatts. So it's 29 times 10 to the minus 6 watts. That's the joules per second being dissipated in the wire. Now, if I want the total energy that was dissipated, I'll call that the change in electrical potential energy. All I've got to do is multiply the rate at which I'm dissipating energy by the length of time over which I've dissipated that energy. Really, this is nothing other than the definition of power. Power is the change in energy divided by the elapsed time. Rearranging it, the dissipated energy is the power times the elapsed time. If I fill in the power, that's 29 microwatts, multiplied by the length of time, that's 600 seconds. I got a value that is 17 millijoules. So 17 times 10 to the minus 3 joules. And so that's the energy that was dissipated in that wire. It's not very much because that wire is a good conductor. That wire has a small resistance. The voltage across the length of the wire is small to drive that current through the wire. The resistance of that wire is small. And so there's not much energy dissipated in that wire. Anyway, this problem was intended as an example on current, and understanding of current from a macro and microscopic viewpoint in terms of the motion of charge, the flow of charge, and also the movement, the motion of electrons. It also involved Ohm's law and the related concepts of resistance, resistivity. And it also involved an important aspect of electrical circuits, that electrical circuits involve energy. And for example, in wires or resistors, you're dissipating it. You're dissipating power. You're turning electrical energy, electrical power into thermal energy, kinetic energy of electrons.